Hello and welcome back. In today's video, we're overclocking the Intel Core i9-13900KS processor all the way up to 6.3 GHz using the ASUS ROG Maximus Z790 Hero motherboard and EK water cooling. In my previous Raptor Lake overclocking guides, I focused a lot on advanced voltage tuning. For this guide, I want to do something slightly different and keep it as simple as possible. Although I will keep my settings as simple as possible, I will still try to provide you an in-depth and detailed overview of how everything works together, frequency and voltage-wise. I hope you enjoy the video. The Intel Core i9-13900KS processor is the flagship processor of Intel's 13th generation Core lineup. It's also touted as the very first 6 GHz desktop CPU. Intel Raptor Lake builds on top of the performance hybrid architecture introduced with the 12th generation Alder Lake, so it also features performance P-cores and efficient E-cores. While it may sound like Raptor Lake is not much different from its predecessor, the spec sheet reads quite impressive. Compared to its Core i9-12900KS predecessor, launched 1 year ago, the 13900KS has a 500 MHz higher turbo boost frequency and 8 additional threads. In this video, we will cover 4 different overclocking strategies. First, we unleash the Turbo Boost 2.0 limits and enable XMP 3.0. Second, we overclock using ASUS AI overclocking technology. Third, we get into simple manual overclocking. Lastly, we fine-tune our manual overclock using Intel's OCTVB technology. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. The Elmo Labs EFC X9 is an evolution of the Elmo Labs EFC I've used in plenty of my SkatterBencher overclocking guides. The X9 supports up to 9 independent PWM fans and can supply 4.5 amps per header or a maximum of 20 amps total. Additionally, there are 2 external temperature sensor connectors plus an onboard ambient temperature and humidity sensor. There's also dedicated EFC software to control the device. As per usual, I map the fan curve to the water temperature and have the fans scale from 0 to 100% fan duty cycle from 25 to 40 degrees Celsius water temperature. The main takeaway from this configuration is that it provides us with a good indication on whether our cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, we must of course check the performance at default settings. Please note that out of the box, the ASUS ROG Maximus Z790 Hero motherboard fully unleashes the Turbo Boost 2.0 power limits. So for us to check the performance of the 13900KS at default, we must first go into the BIOS and go to the Extreme Tweaker menu. Set ASUS Multi-Core Enhancement to Disabled and Force All Limits. Then save and exit the BIOS. The default Turbo Boost 2.0 parameters for the Core i9-13900KS are as follows. Here is the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 5107 MHz and the average CPU E-core clock is 3926 MHz with 1.079 volts. The average CPU temperature is 84 degrees Celsius. The ambient and water temperature is 25.7 and 29.9 degrees Celsius. The average CPU package power is 252.9 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5357 MHz and the average CPU E-core clock is 4250 MHz with 1.191 volts. The average CPU temperature is 84 degrees Celsius. The ambient and water temperature is 25.3 and 28.7 degrees Celsius. The average CPU package power is 252.9 watts. Now let us try our first overclocking strategy. But before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. However, it does not delete any of the BIOS profiles previously saved. In our first overclocking strategy, we will take advantage of unleashing the Turbo Boost 2.0 power limits and enabling Intel Extreme Memory Profile 3.0. Intel Turbo Boost 2.0 is an Intel technology that allows your processor to run faster than base specifications. It does this when the processor is running within the thermal, power, and current specification limits. The ultimate advantage is, of course, improved system performance in both multi-threaded and single-threaded workloads. The Turbo Boost algorithm works according to a proprietary EWMA formula. This stands for exponentially weighted moving average. There are 3 parameters to consider: PL1, PL2, and tau. Of course, Turbo Boost 2.0 is present on Raptor Lake CPUs, as it's the primary driver for performance over the base specification. Similar to Alder Lake, but a significant change from any previous Intel Core processors is that, at least for the K-SKU CPUs, PL1 is by default equal to PL2. This change effectively means that Intel has enabled near unlimited peak turbo by default. The maximum performance of your system is therefore entirely limited by your cooling solution. If your cooling solution is insufficient, then the processor will throttle the frequency and the associated performance at TJ max. For Raptor Lake CPUs, the TJ max is 100 degrees Celsius. An easy ASUS multi-core enhancement option on ASUS motherboards allows you to unleash the Turbo Boost power limits. Set the option to Enabled Remove All Limits to enjoy the maximum performance. Adjusting the Turbo Boost power limits is, strictly speaking, not considered overclocking. And that's because we don't change any of the frequency, voltage, or temperature parameters. Intel provides the Turbo Boost power limits or power parameters to motherboard vendors and system integrators to ensure their designs enable the base performance of the CPU. But as we all know, better motherboard designs, better cooling solutions, and better system designs can enable peak performance for much longer. Intel Extreme Memory Profile, or XMP, is an Intel technology that lets you automatically overclock your system memory to get better performance. It is built on top of the JEDEC specification and allows memory vendors such as G.Skill to program higher performance parameters on the memory sticks. Intel Extreme Memory Profile 3.0 is the new XMP standard for DDR5 memory. It is primarily based on the XMP 2.0 standard for DDR4, but has additional functionality. There's a lot more to the XMP 3.0 standard that's outside of the scope of this video. If you want to learn more about XMP 3.0, feel free to check out my Alder Lake launch video. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to XMP2. Set ASUS Multi-Core Enhancement to Enabled Remove All Limits. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. As expected, since we're not increasing the frequency of the CPU cores, the performance improvement is relatively limited. That said, improving the memory performance by using XMP 3.0 does help in memory-sensitive benchmark applications. We see the highest performance improvement of plus 11.88% in Geekbench 5. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 5204 MHz and the average CPU E-core clock is 4120 MHz with 1.119 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 26.4 and 31 degrees Celsius. The average CPU package power is 310 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5456 MHz and the average CPU E-core clock is 4299 MHz with 1.206 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 26.5 and 30.7 degrees Celsius. The average CPU package power is 315.2 watts. In our second overclocking strategy, we will leverage the ASUS AI overclocking feature and XMP tweaked setting embedded in the ASUS ROG BIOS. ASUS AI overclocking is a unique approach to automatic overclocking. Rather than working with profiles that have a certain frequency or a voltage, the system will monitor the CPU and cooling system throughout an initial testing phase. Based on its findings, it will then predict the optimal settings. There are 3 steps to enabling AI overclocking. First, reset the BIOS to default settings, then reboot and enter the operating system. Run a couple of heavy workloads, such as Cinebench R23, RealBench or Intel XTU for 10 to 30 minutes, then return to the BIOS and enter the AI OC guide menu from the top. Make sure to read through the explanation and click Enable AI when ready. In addition to automatic overclocking, AI overclocking provides a lot of advanced information and suggestions in the AI features menu. The information includes the following. The SP value is based on the combination of maximum boost frequency, temperature, and P0 VID. Generally, it indicates the quality of a particular core. A higher SP value would indicate a better quality core with superior overclocking capabilities, though it's not an exact science. There are a couple of additional options that allow you to fine-tune your AI overclock, including one which we'll use in this OC strategy. Optimized AVX frequency allows you to toggle between normal use and heavy use, where heavy use should be selected if you're running extreme workloads like Prime 95 with AVX enabled. After enabling AI overclock and adjusting the optimized AVX frequency, the following settings have changed. XMP tweaked is a new setting under the AI overclock tuner option in addition to XMP1 and XMP2. All 3 settings load the memory kit XMP profile but do it slightly differently. In this OC strategy, I use XMP tweaked instead of the XMP2 that I normally use. Upon entering the BIOS, go to the Extreme Tweaker menu. Enter the AI Overclocking Guide menu. Go through the guide, then click Enable AI. Set AI Overclock Tuner to XMP Tweaked. Set Optimized AVX Frequency to Heavy AVX, then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. With AI overclocking, we increased the processor frequency slightly over the stock settings from 6 GHz to 6.3 GHz P-cores. Therefore, we expect a slight performance uplift, which we see in the benchmark results. The performance uplift from AI overclocking is surprisingly good. We have the best performance improvement of plus 23.35% in Geekbench 5. A quick note on the CPU-Z single-thread performance. The hardware P-state registers adjust the core priority ranking when you change the CPU ratios, essentially ensuring that the highest clocked core has the highest priority. However, the CPU-Z benchmark seems to ignore this core reprioritization and instead forces the workload to run on a favored core. The AI overclock for this configuration sets the per core ratio limit of P-core 4 to 58x, which is lower than the default 60x, hence the lower performance. When running Prime 95 small FFTs with AVX2 enabled, unfortunately, the CPU is not stable. That's not surprising since AI overclock is designed for typical workload scenarios and not extreme workloads like Prime 95 with AVX2 enabled. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5540 MHz and the average CPU E-core clock is 4300 MHz with 1.156 volts. The average CPU temperature is 95 degrees Celsius. The ambient and water temperature is 25.7 and 30.7 degrees Celsius. The average CPU package power is 291.5 watts. In our third overclocking strategy, we will pursue a simple manual overclock. The manual overclock primarily relies on configuring the turbo ratios and setting an adaptive voltage. As I mentioned in the beginning of my video, I will try to keep the configuration itself as simple as possible. However, I will dig into the details of what's going on behind the scenes, so you have a good understanding and a lot of context to go about your own overclocking tuning. Generally speaking, on an Intel platform, there are 2 ways to configure the CPU ratios: sync all core or by using the turbo ratio configuration. Sync all cores sets a single fixed ratio applied to all cores. This is very much the historical way of Intel CPU overclocking. Turbo ratio configuration allows us to modify the default Intel frequency specification and configure an overclock for a dynamic scenario. Before we go any further, there are 3 critical elements of any turbo ratio configuration that you need to be aware of. 1. You can configure the maximum allowed CPU core ratio for any number of active cores. 2. You can configure the maximum allowed CPU core ratio for a given CPU core. And 3. The turbo ratio configuration for the P core and E cores is independent. To explain the first point, let's take the default configuration of the 13900KS. The 13900KS has a total of 8 P cores. Therefore, we can configure the maximum allowed P core ratio for when 1 P core is active, when 2 P cores are active, all the way up to when all 8 P cores are active. The standard configuration allows every P core to boost to 5.6 GHz when all cores are active. In our overclock, we adjust the turbo ratio configuration to boost to 6.2 GHz when up to 4 P cores are active, and to 5.7 GHz when up to 8 P cores are active. To explain the second point, again, let's consider the 13900KS default specification. While the 13900KS has 8 identical P cores, 2 of those cores are called the favored cores. The maximum allowed frequency for the favored cores is 6 GHz, whereas the other cores are limited to 5.6 GHz. Often we use the per core ratio limit to prevent the weaker cores from boosting to the highest turbo ratio. For example, in this OC strategy, I prevent core 1 and core 7 from boosting to 62x. I allow core 1 to boost to 61x and core 7 to boost to 60x. All the other cores can boost to 62x. To explain the third point, again, let's refer to the 13900KS. The CPU has a total of 8 P cores and 16 E cores. While the P cores can boost up to 6 GHz, the E cores can only boost up to 4.3 GHz. The P core rules for maximum allowed frequency can also be applied to the E cores, however, with one major caveat. The E-core CPU ratio can only be controlled in groups of 4 E-cores. So for the 13900KS, since it has 16 E-cores in total, we can configure the maximum allowed core ratio for a total of 4 groups of 4 E-cores. However, we can still configure the maximum allowed frequency for 1 active E-core up to 16 active E-cores. We also increased the E-core frequency from 4.3 GHz to 4.5 GHz in this OC strategy. Before we move on to the voltage side of the configuration, let's first spend a couple of minutes talking about TJ Max and thermal throttling. T-junction max, or TJ Max, is the maximum temperature that your CPU is allowed to operate at. Internal control mechanisms will reduce the CPU frequency if the operating temperature is above the TJ Max. The TJ Max for Raptor Lake CPUs is 100 degrees Celsius. However, it can be manually increased to 115 degrees Celsius, though that's not recommended for long-term use. The maximum operating temperature for your CPU is a sensitive topic in the PC enthusiast space. In the next couple of minutes, I want to dispel 2 myths related to TJ Max. 1. Running at TJ Max is extremely dangerous. 2. Thermal throttling causes severe performance degradation. The first myth is that it's absolutely unsafe to run your processor at TJ Max. I often get questions or comments when I show my Prime 95 results, where the CPU is typically running at the maximum allowed temperature. I get questions such as, is this really safe? Or I get told that it's extremely risky to run the processor at that temperature. The irony of those comments is that the operating temperature is the most conservative part of my overclocking guides. It's the one parameter that I don't run out of spec. For this 13900KS, Intel says I can run all cores at 5.6 GHz with 1.38 volt up to 100 degrees Celsius. And in my OC strategies, I increase the frequency and the voltage, but maintain the maximum of 100 degrees Celsius specification. The bottom line is that Intel puts its money where its mouth is. Intel makes a legal commitment by its 3-year warranty that your processor will perform according to its specification, which includes an operating temperature of up to 100 degrees Celsius. The second myth is that thermal throttling severely degrades your compute performance and must be avoided at all costs. While that may have been true a decade ago, the truth is that modern CPUs have very advanced performance maximizing technologies that are designed to maximize the performance in any scenario, including a scenario where your CPU is running at the maximum allowed temperature. The Raptor Lake TJ Max thermal throttling mechanism is quite simple. When the operating temperature reaches TJ Max, the CPU reduces the CPU turbo ratio until the temperature is below TJ Max. In my overclocking strategies, I try leveraging those technologies to squeeze the most performance out of my system, before the thermal throttling point and at the thermal throttling point. That's why you will see me report on my Prime 95 overclocking results, and specifically the frequency, and how you will see me try and improve that frequency, as well as try and improve the performance in the normal benchmark workloads. On Raptor Lake processors, the user can configure the TJ Max between 62 and 115 degrees Celsius. To illustrate the performance throttling, I tested the 13900KS with P cores at 5.8 GHz and E cores at 4.5 GHz in Cinebench R23. As you can see from the data, when TJ Max is set to 62 degrees Celsius, you lose about 15% performance due to thermal throttling compared to when the TJ Max is at its default of 100 degrees Celsius. To illustrate the frequency throttling behavior, I set the TJ Max to 62 degrees Celsius and ran Cinebench R23. As you can see from the data, the CPU almost instantaneously responds to a temperature exceeding TJ Max by reducing the P-core frequency from 5.8 GHz to 4.7 GHz and the E-core frequency from 4.5 to 3.7 GHz. As a side note, ASUS also has its own TJ Max style thermal throttling technology. You can use it by enabling the package temperature threshold option in the BIOS. This technology will monitor the ASUS calibrated socket temperature and lower the Turbo Boost 2.0 PL1 limit if it exceeds the target temperature. Limiting the CPU power consumption will also reduce the operating temperature. While ASUS technology works pretty well, it is less accurate and responsive than Intel's TJ Max mechanism. To illustrate the frequency throttling behavior, I set TJ Max to 115 degrees Celsius and the package temperature threshold to 62 degrees Celsius and ran Cinebench R23. As you can see from the data, the CPU responds much slower to the change in operating temperature than TJ Max. At the start of the benchmark, the CPU temperature spikes up high, even above 100 degrees Celsius, before the ASUS technology aggressively adjusts the power limit to reduce the temperature. The temperature first drops significantly below the 62 degrees Celsius target, then gradually increases as the ASUS algorithm adjusts the power limit. The actual CPU package temperature with this setting is around 75 degrees Celsius. While I try to dispel the myth that running at the TJ Max thermal throttling point will severely impact your system's performance, it does contain an element of truth. As we've seen from the data, when you run at the thermal throttling point, the performance will go down. So that's why it's so important to pair your powerful CPU with a cooling solution that's adequate so that you avoid thermal throttling too early and you can maximize the performance even at the thermal throttling point. Voltage tuning, and then very specifically undervolting, is the primary avenue to squeeze more performance out of your Raptor Lake i9 processor. And that's because, of course, the CPU is designed to push the performance all the way to the thermal throttling point. By undervolting, we can reduce the power consumption, and therefore we reduce also the temperature at a certain frequency. And when we reduce the temperature at a certain frequency, we create headroom for higher frequency. On Raptor Lake, the VCC-IA voltage rail drives the voltage for the CPU cores, P-core and E-cores, and the ring. That means a single voltage is used for all these parts of the CPU. How that voltage is configured is straightforward yet complex. There are three elements to how the CPU voltage is configured on your system: the CPU, the motherboard design, and the VRM controller. Let's start with the CPU side of the story. An Intel CPU relies on a lot of factory-fused voltage frequency curves to manage the dynamic performance behavior of the CPU. A lot of parts inside your CPU have a VF curve, including those that affect the VCC-IA voltage rail. In the case of the Core i9-13900KS, the VCC-IA voltage rail is affected by no less than 13 different voltage frequency curves. For this guide, I extracted the voltage frequency curves of this specific 13900KS. Based on these VF curves, to get a specific voltage provided via the VCC-IA voltage rail, the CPU issues an SVID request to the voltage controller. The VID requested is the highest among all the requested voltages according to every VF curve affecting the voltage rail. Let's take an example. The highest voltage requested according to the relevant VF curves is 1.34 volt by P-core 0. This will be the VID request to the voltage controller. Here's another example. In this case, the highest voltage requested according to the relevant VF curves is 1.28 volt by E-core group 0. This will be the ISVID request to the voltage controller. The goal of the ISVID voltage request from the CPU to the voltage regulator is that the effective voltage at the CPU die is equal to the requested voltage. However, as overclockers and enthusiasts know very well, that's not always the case. That's because there are a lot of electrical components between the voltage regulator and the CPU die. To avoid a situation where the voltage delivered to the CPU die is significantly lower than what is requested by the CPU, we essentially have two tools, the AC/DC load line and the VRM load line. The AC/DC load line is designed for motherboard engineers to bring into the voltage frequency equation the electrical impedance of the motherboard. Electrical impedance is the opposition to alternating current, and it is impacted by the motherboard design, the PCB quality, and so on. Electrical impedance can significantly affect the effective voltage at the CPU die. Therefore, there may be a significant difference between the requested and effective voltage. We can define the AC/DC load line parameters to account for this difference. Adjusting the AC load line offsets the requested voltage, defined by the factory-fused voltage frequency curve, to account for any electrical impedance. Adjusting the DC load line informs the CPU about the expected effective voltage at the CPU die. The VRM load line is important for two reasons: V-droop and undershoot. V-droop is the decrease in voltage when the CPU goes from idle to load. You want your CPU to be stable in all scenarios, so knowing the lowest voltage the CPU runs at is very important. After all, if the voltage is too low, the overclock won't be stable. Undershoot and its counterpart overshoot is a brief voltage spike that occurs when the CPU switches from idle to load or from load to idle. These spikes cannot be measured easily and usually require an expensive oscilloscope to detect. I highly recommend the Elmore Labs article titled VRM Load Line Visualized to see a great picture of undershoot and overshoot in action. While undershoot and overshoot are very temporary spikes, an undershoot that is too low can still cause instability. The VRM load line is relevant for our overclocking strategy for two reasons. First, it helps control the voltage in heavy workloads. Enthusiasts often rely on VRM load line tuning to decrease the voltage in a heavy workload, which yields lower power consumption and operating temperatures. Second, since the VRM load line can significantly affect the effective CPU core voltage, we must account for it when setting the DC load line. Since we are keeping the voltage configuration as simple as possible for this overclocking guide and this overclocking strategy, we will rely on the motherboard auto rules. Auto rules are essentially automatic changes to BIOS settings when you make certain changes in the BIOS. This ASUS motherboard in particular sets the AC/DC and VRM load lines when the user is configuring the turbo ratios manually. In my specific case, the auto rules make the following adjustments. As discussed, the VRM load line will affect the V-droop, which is the voltage drop under load. To illustrate this, I compare the effective voltage in idle and load to the voltage frequency curve. As you can see from the chart, the effective voltage under load is significantly lower than what we would expect from the voltage frequency curve. In practical terms, it means that we're already undervolting the CPU. Unfortunately, we are undervolting too aggressively with the motherboard auto rules, and the system isn't stable at 5.7 GHz in an all-core workload. So to counter this, I will make one small adjustment. I will set the VRM load line to level 6. This will lessen the V droop, so it will reduce the drop in voltage going from idle to load. Also, the ASUS motherboard auto rules make changes to the AC/DC load line. Again, I plot the voltage in idle and load scenarios. You can see that the voltage under load has significantly increased from the auto rule configuration, but is still considerably lower than the factory fused voltage frequency curve. With this configuration, 57X was stable in medium load all-core workloads, though the voltage is too high to stay below TJ max when running Prime 95. One last thing I want to highlight. Did you notice that the idle voltage for ratios 60X, 61X, and 62X is 1.465 volt instead of the expected 1.435 volt? That's not a hardware info reporting error or related to the load line configuration, but rather a curiosity with the ring voltage. Before I can add more detail to this curiosity, we have to talk about Intel adaptive voltage mode. On Intel platforms, there are two main ways of configuring the CPU core voltage: override mode and adaptive mode. Override mode specifies a single static voltage across all ratios. It is mainly used for extreme overclocking purposes, where stability at high frequencies is the only consideration. Adaptive mode is the standard mode of operation. In adaptive mode, the CPU relies on the VF curves to set the appropriate voltage for the VCC-IA voltage rail. Both override and adaptive mode settings can be configured via the CPU registers. So, in effect, we control the CPU VID request to the voltage controller. This is Intel's intended way of overclocking. Of course, most voltage controllers also allow independent configuration. For example, they enable us to configure a voltage offset to the requested voltage. For the purpose of this guide, however, let's ignore the capabilities of the voltage controllers and focus on Intel's intended way of overclocking. We can specify a voltage offset for override and adaptive modes. Of course, this doesn't make much sense for override mode. If you set 1.35 volt with a 50 mV offset, you might as well set 1.4 volt, but it can be helpful in adaptive mode. As I mentioned, Intel offers great granularity for tuning the many VF curves inside the CPU. Let's forget about the E-cores and ring to keep things simple and assume a case where we set a global adaptive voltage for the CPU P-cores. Now, let's dig into what happens when we set a global adaptive voltage. First, disregarding any user-set global or VF point offsets, the adaptive voltage set in the BIOS is mapped against what's called the OC ratio. The OC ratio is the highest ratio configured for the CPU. When you leave everything at default, the OC ratio is determined by the default maximum turbo ratio. When you manually overclock, the OC ratio is the highest ratio you configure across all the various settings and options. Second, specific rules govern what adaptive voltage can be set. The voltage set for a given ratio n must be higher than or equal to the voltage set for ratio n-1. Suppose our 13900KS runs 60X at 1.43 volt. In that case, setting the adaptive voltage mapped to 60X lower than 1.43 volt is pointless. 60X will always run at 1.43 volt or higher. The adaptive voltage configured for any ratio below the maximum default turbo ratio will be ignored. Take the same example of the 13900KS, specified to run 60X at 1.43 volt. If you try to configure all cores to 57X and set 1.2 volt, the CPU will ignore this because it has its own factory-fused target voltage for all ratios up to 60X and will use that voltage. For ratios between the OC ratio and the next highest factory-fused VF point, the voltage is interpolated between the set adaptive voltage and the factory-fused voltage. Returning to our example of our 13900KS specified to run 60X at 1.43 volt, let's say we manually configure the OC ratio to be 65x at 1.5 volt. The target voltage for ratios 61, 62, 63, and 64x will now be interpolated between 1.43 volt and 1.5 volt. So in conclusion, the adaptive voltage mode set in the BIOS is mapped against what's called the OC ratio. The OC ratio is either the highest default turbo ratio of your CPU or the highest turbo ratio you've programmed across all of the settings, including per core ratio limit, OCTVB, and so on. The voltage for ratios lower than the OC ratio is either set by the factory fused voltage frequency point, or if there is no VF point, interpolated between the next and previous factory fused voltage frequency point. A feature Intel introduced with Alder Lake that's been flying under the radar is per core voltage. To make a long story short, we can independently program an adaptive voltage for each individual core. If we program the adaptive voltage for a specific core, it is mapped against that core's OC ratio, which is the per core ratio limit. The same principle also applies to the E-core groups and ring, by the way. For this OC strategy, I use an adaptive voltage of 1.435 volt. Now let's return to the ring voltage curiosity I mentioned before. Since we use an adaptive voltage of 1.435 volt for 62x, we'd assume this be the effective voltage in idle at 62x. But looking at the voltage frequency curves, it seems the voltage is more like 1.465 volt. To make a long story short, I have no clue what's going on, but here's what kind of looks like going on. When we set the adaptive voltage for the CPU cores, it also sets this adaptive voltage for the ring. When we check hardware info, the ring VID is 1.435 volt, precisely as we set for the cores in the BIOS. Then it seems there's some kind of a rule where the core VID must be a minimum of 30 millivolts higher than the ring VID. That shows up as 1.465 volt VID in hardware info. Why and how, as I said, I have no idea. I've confirmed this behavior also on a 13900K, so it remains a Raptor Lake mystery. Once I find out the reason, if I ever do, I'll be sure to let you guys know. We set an AVX negative ratio offset of 5, reducing the CPU frequency in some AVX workloads. While AVX negative ratio offset has been on Intel CPUs for ages, since Alder Lake there have been a couple of changes in the behavior. I discussed that in previous Raptor Lake guides. The long story short is that the AVX offset doesn't apply to all AVX workloads, such as Cinebench R23. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to XMP2. Set ASUS Multicore Enhancement to Enabled Remove All Limits. Set DRAM frequency to DDR5 7600 MHz. Set Performance Core Ratio to by core usage. Set 1 core to 4 core ratio limit to 62. Set 5 core to 8 core ratio limit to 57. Enter the specific performance core submenu. Set performance core 0, 2, 3, 4, 5, and 6 specific ratio limit to 62. Set performance core 1 specific ratio limit to 61. Set performance core 7 specific ratio limit to 60. Leave the specific performance core submenu. Set efficient core ratio to sync all cores. Set all core ratio limit to 45. Enter the AVX related controls submenu. Set AVX2 ratio offset to per core ratio limit to user specify. Set AVX2 ratio offset to 5. Leave the AVX related controls submenu. Enter the Digi Plus VRM submenu. Set CPU load line calibration to level 6. Leave the Digi Plus VRM submenu. Set global core SVID voltage to adaptive mode. Set offset mode sign to plus. Set additional turbo mode CPU core voltage to 1.435. Set high DRAM voltage mode to enabled. Set DRAM VDD voltage to 1.45. Set DRAM VDDQ voltage to 1.45. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. Even though we only slightly increased the single and all-core P-core boost frequency, thanks to the aggressive undervolting, we're seeing a decent performance uplift across the board. We see a maximum multi-threaded performance improvement of 21.20% in Geekbench 5. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 5274 MHz, and the average CPU E-core clock is 4175 MHz with 1.111 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 25.9 and 31.9 degrees Celsius. The average CPU package power is 308.8 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5533 MHz, and the average CPU E-core clock is 4494 MHz with 1.19 volt. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 25.7 and 30.7 degrees Celsius. The average CPU package power is 313.6 watts. In our fourth and final overclocking strategy, we resort to advanced manual tuning using Intel's Overclocking Thermal Velocity Boost toolkit. Our objective is simple: squeeze a little bit more frequency out of the chip and get a little bit more performance in light workloads. In 2018, Intel introduced the Thermal Velocity Boost technology with the launch of the Core i9-8950HK Coffee Lake mobile processor. And ever since, it's been an indispensable feature on Intel Core processor. Thermal Velocity Boost does two things. First, it decreases the operating voltage if the CPU temperature is below TJ max. And two, it opportunistically increases the clock frequency above the Turbo Boost 2.0 and 3.0 frequencies based on how much the processor operates below its maximum temperature. With the introduction of cryo-cooling in 2020, Intel opened up the TVB configuration to motherboard vendors. The feature is called Overclocking Thermal Velocity Boost, or OCTVB for short. The easiest way to think of OCTVB is limiting, or clipping, the maximum allowed CPU ratio based on the CPU operating temperature. OCTVB is based on the by-core usage turbo ratio configuration. For each number of active cores, you can define two temperature points, each with a unique number of downbins. A downbin is essentially the number of ratios you want to drop. Let's take the configuration of this OC strategy. When one P-core is active, the base ratio is 63x, so the frequency will be 6.3 GHz. However, when the temperature is 68 degrees Celsius, the ratio is clipped by 1x. That means the maximum ratio is now 62x. When all 8 P-cores are active, the base ratio is 61x, so the frequency will be 6.1 GHz. However, when the maximum temperature is 75 degrees Celsius, the ratio is clipped by 2x. That means the maximum ratio is now 59x. When the temperature hits 85 degrees Celsius, the ratio is clipped once more by 1x. So the resulting maximum ratio is now 58x. Note that we have TJ max configured at the default of 100 degrees Celsius. So beyond 100 degrees Celsius, the CPU will automatically reduce the frequency to stay within the thermal limit. Testing an OCTVB configuration is notoriously tricky, and that's because we can't simply run our extreme workloads and see if it works. It would just push the CPU beyond the temperatures where our OCTVB is configured. So essentially, the only thing you can really do is run through your benchmark suite and see if there's any instabilities. However, as I've shown in other SkatterBencher guides, we can use the thermal velocity boost voltage optimization to get an idea of how much extra frequency we can get with how much lower temperature. Upon entering the BIOS, go to the Extreme Tweaker menu. Set AI Overclock Tuner to XMP2. Set ASUS Multi-Core Enhancement to Enabled Remove All Limits. Set DRAM Frequency to DDR5 7600 MHz. Set Performance Core Ratio to by-core usage. Set 1-core to 3-core ratio limit to 63. Set 4-core to 6-core ratio limit to 62. Set 7-core and 8-core ratio limit to 61. Enter the specific performance core submenu. Set performance core 0, 2, 3, 5, and 6 specific ratio limit to 63. Set performance core 1 and core 7 specific ratio limit to 61. For each performance core, set specific voltage to adaptive mode. For each performance core, set offset mode sign to plus. For each performance core, set additional turbo mode CPU voltage to 1.475. Leave the specific performance core submenu. Set efficient core ratio to sync all cores. Set all core ratio limit to 45. Enter the specific efficient core submenu. For each efficient core group, set specific ratio limit to 45. For each efficient core group, set specific voltage to adaptive mode. For each efficient core group, set offset mode sign to plus. For each efficient core group, set additional turbo mode CPU voltage to 1.3. Leave the specific efficient core submenu. Enter the AVX related controls submenu. Set AVX2 ratio offset to per core ratio limit to user specify. Set AVX2 ratio offset to 6. Leave the AVX related controls submenu. Enter the DigiPlus VRM submenu. Set CPU load line calibration to level 6. Leave the DigiPlus VRM submenu. Enter the thermal velocity boost submenu. Set TVB voltage optimizations to disabled. Set enhanced TVB to disabled. Set overclocking TVB to enabled. Set 1 core to 8 core active to enabled. For 1 core and 2 core active, set temperature A to 68. For 3 core to 5 core active, set temperature A to 70. For 6 core active, set temperature A to 60. For 7 core and 8 core active, set temperature A to 75. For each core active, set negative ratio offset A to user specify. For 1 core to 6 core active, set ratio offset A to 1. For 7 core and 8 core active, set ratio offset A to 2. For 1 core and 2 core active, set temperature B to 115. For 3 core to 6 core active, set temperature B to 90. For 7 core and 8 core active, set temperature B to 85. For each core active, set negative ratio offset B to user specify. For 1 core and 2 core active, set ratio offset B to 0. For 3 core to 8 core active, set ratio offset B to 1. Leave the thermal velocity boost submenu. Set global core ISVID voltage to adaptive mode. Set offset mode sign to plus. Set additional turbo mode CPU core voltage to 1.475. Set high DRAM voltage mode to enabled. Set DRAM VDD voltage to 1.45. Set DRAM VDDQ voltage to 1.45. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. While this OC strategy allows us to squeeze more frequency out of our CPU, it won't improve the performance in all scenarios because it's configured through OCTVB. In fact, the performance improvements should only appear in light workloads, such as the 3DMark CPU profile, which doesn't push the CPU to the TJ max. We see the highest performance improvement of plus 21.21% in Geekbench 5. When running Prime 95 small FFTs with AVX2 enabled, the average CPU P-core clock is 5281 MHz and the average CPU E-core clock is 4262 MHz with 1.112 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 25.4 and 31 degrees Celsius. The average CPU package power is 310.3 watts. When running Prime 95 small FFTs with AVX disabled, the average CPU P-core clock is 5538 MHz and the average CPU E-core clock is 4439 MHz with 1.193 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperature is 25 and 30.5 degrees Celsius. The average CPU package power is 312.9 watts. Alright, let's wrap this up. Overclocking the Core i9-13900KS isn't really that much different from overclocking any other Core i9 Raptor Lake CPU. The way you get more performance is Undervolt, enable XMP, and unleash your Turbo Boost 2.0 power limits. I tested a couple of Core i9-13900KS CPUs and it seems that, on average, they're slightly better than the 13900Ks. But that's not to say that a great 13900K wouldn't be better than an average 13900KS. After all, the first 9 GHz CPU is a 13900K. What I find most extraordinary about this overclock is that I was able to run an all-core yet light workload at above 6 GHz. That's amazing, but at the same time, it's also something that we are now used to with Raptor Lake. And that tells you a lot about how amazing the Raptor Lake architecture is for high frequency. Anyway, that's it for this video. I want to thank you for watching, and of course I want to thank my patrons for the support. As per usual, I will have a written version of this video up on my blog, so if you want to read through the BIOS settings or check the benchmark results, you can go over there, and see you next time. Have a good one.